Grade 10s. We have to start off with Unit 7, the building blocks of matter. It's page 115. At the top, the introduction, everything around us is made up of atoms. Atoms, molecules, and ions are the building blocks of all materials. People, I think in grade 6 or 7 in science, you were taught that matter is anything that has mass and occupies space. All right. Now, when we did the kinetic theory, the first thing on that theory tells us all matter consists of particles. Now, what we are going to have a look at in this module is what are these particles? Now, depending on what we have, we know we get different types of bonds. You've done covalent bonding and you've done ionic bonding. Now, another one that we will be doing soon is metallic bonding. But now, depending on the type of bonding, it depends on what particles make up the substance. We know, for example, if I have a covalently bonded substance, we refer to those particles as molecules. If I have an ionically bonded substance, the particles in a salt we refer to as ions. Okay. So, just in general, the particles that we get are atoms, ions, or molecules. All right. All right. People, just definitions. There's nothing new over here. An element is very simply a pure substance. Now, what's the difference between pure and impure? We've done it in the previous chapter. Pure substances have a fixed melting and boiling point. They have a fixed ratio. They are either elements or compounds. Okay? They are made up out of one type of particle. If it's water, we're referring to the particle is H2O. If it is oxygen, we're referring to the particle is O2. All right. So elements then are pure substances that consist of one kind of atom. Remember, the atoms that we have are found on the periodic table. All right. You'll always be given a periodic table. You must just sort of know how to use it. So, one kind of atom, and it cannot be broken down further by chemical means. Technically speaking, we can break an atom down, all right? But then we go to subatomic particles. If I go and break an atom apart, I end up with protons, neutrons, and electrons. Now, if I broke an atom of sodium apart, and I put all the protons in a bucket, and all the neutrons in a bucket, and all the electrons in a bucket, and then I went and took an atom of gold, and I broke it apart, and I took all those protons, and I threw it into the same bucket with the other protons, all the neutrons into the neutron bucket, and the electrons into the electron bucket. If I picked up a proton from the proton bucket, I wouldn't be able to say from which element it came. You understand? So, technically speaking, when we talk about the particles that matter is made up out of, we don't go to subatomic level. All right, so we then say that an element cannot be broken down by chemical means. Okay. All right, so mixtures. Mixtures, people, are impure, meaning it consists of more than one thing. If I want to bake a cake, if I have had someone mix the sugar and the salt in a bag, and I have to bake that cake using that sugar or salt, I wouldn't be able to say how much sugar or how much salt I'm using. It's not going to work. All right, it's not pure. My recipe won't work out. So, mixtures are impure. It consists of two or more kinds of substances. Now, these substances can be elements and elements. All right, it can be elements and compounds, or it can be compounds and compounds. Do you understand? And it is varying amounts in varying quantities. So we say then they are impure, two or more kinds of substances, and they are physically combined. In other words, there are no chemical bonds holding them together. If I take a bag of salt and I mix it with a bag of sugar, I've got a mixture of sugar and salt, But the sugar crystals are still uniquely sugar, and the salt crystals are still uniquely salt. They haven't gone and stuck onto each other by some or other method. All right, they are still separate from each other. There are no chemical bonds, so then we say we can separate them using physical processes. That would be sorting by hand or filtering or dissolving it in a solvent and then filtering the one that doesn't dissolve, etc. Okay, no chemical bonds are involved. Then, as a subheading under mixtures, what is an alloy? Molten mixture of metals. So are alloys pure? No, not in the technical sense in chemistry. Alloys can be made by mixing other metals in. Whether I mix a teaspoon of the other metal or whether I mix a bucketful of the other metal, I've got a mixture. You follow? Okay, so alloys are mixtures of metals and other elements, but it's very important. It is a mixture. We'll come back to that when we do the metals. All right. Compounds. The next one is a pure substance. All right. Can you see compounds and elements are pure? All right. Pure substances consisting of two or more elements chemically bonded. For example, ammonia consists of nitrogen bonded onto hydrogen. But between the nitrogen and the hydrogen there are chemical bonds. We know they are non-metals, so we know what type of chemical bond would be between the nitrogen and the hydrogen? A covalent one, the one where we share electrons. If I look at something like this, it's the chemical formula for vinegar. Carbon, hydrogen, and oxygen. It's 3 different elements. Now, this is an organic compound, so we write it in a slightly different way. All right. But all of these atoms, carbon and hydrogen and oxygen, they are chemically bonded. Also non-metal, so it will also be covalent bonds, bonding them together. Okay, so compounds, pure substances, 2 or more elements that are chemically bonded. Now the formula of a compound, for example NH3, CH3, COOH, that formula tells us in the first place which elements, all right? So which elements do we have over here? Carbon, hydrogen, and oxygen. Which elements do we have over here? Nitrogen and hydrogen. You follow me? Okay? So which elements we have? It also tells us the exact proportion, let me do that, of each element in the compound. For example, in ammonia, the proportion of nitrogen is 1 to hydrogen 3, always. If I have a different proportion, if I had, for example, NH4, then I no longer have ammonia. I've got something else. Then I've got the ammonium ion. All right. So the formula tells me exactly how many atoms of each element is in that compound. All right. And then just an example here, water, H2O. We know which elements, hydrogen and oxygen. We know the proportion, well, it's 2 hydrogens for every 1 oxygen. All right. That then about the formula of a compound. Now, we're going to have a look at the reaction of sulfur with iron. Now, I'm going to come back to that in a moment, all right? Because there's a video clip, and I first want to finish up, and then we will do the video clip. Okay, but what this part is about is that I can take 2 elements, iron and sulfur, that normally is fairly harmless, lying around in a laboratory or wherever. Sulfur, iron is a metal, shiny, grey. We get iron filings. There will be darkish little splinters of iron. Sulfur is a non-metal, and I don't know if you've ever seen sulfur. You can buy them at Agra in buckets. It's a yellow powder. All right? They sometimes use it to treat funguses on plants, etc. Okay? So sulfur is a yellow powder. When I add them and I mix them up in a cup, nothing's going to happen. But if I went and I mixed them up in a fairly specific proportion, all right, and I go and I heat it, all right, I've got it in a beaker and I heat it, we find that a chemical reaction occurs. And we can see this chemical reaction happen because the reaction that happens when it gets going, it's exothermic and it gives off heat, and we can see this heat as a red glow that spreads through the mixture. And you can feel the mixture, it becomes very hot. All right. That is what the video clip will show us. So, just very simply, iron is a grey metal. Sulfur is a yellow non-metal. Iron filings will be magnetic. I could pull them out with a magnet from the yellow powder. All right? The yellow powder is not magnetic. So they say when these two elements are mixed and then heated, we get a chemical reaction. What is very important when there is a chemical reaction? It implies we are making and or breaking chemical bonds. Very important. A chemical reaction implies the making and or breaking of chemical bonds. So, starting off, they tell us that there is a red glow that spreads through the mixture. An exothermic reaction is one that gives off energy. The energy is normally in the form of heat, or we can see it as light, or it can be sound. Okay, chemical reactions mostly heat or light. We get a new substance, iron sulfide. Iron sulfide looks different to the iron filings and to the yellow color of the sulfur that it originally was made up out of. And we will see in the video clip, it's like a dark brown, blackish substance that is formed. All right, if you tested it with a magnet, we will find iron sulfide is not at all magnetic, even though it contains iron. But now we get new properties, because over here we have a new substance. This iron sulfide will have its own specific melting and boiling point. It will have its own specific density that will differ from that of iron and sulfur, because once we get new chemical bonds, the stuff changes and it forms something unique. Okay, a new compound is formed, and this compound is different from the elements, iron and sulfur, that were mixed together to make it. Which brings us then to a comparison between mixtures and compounds. Now, don't go and confuse this. In one of the previous units, we had a look at pure and impure. There is overlap, because pure substances are elements and compounds. All right, mixtures are impure. But now specifically, we're going to have a look at mixtures and compounds. You can go and say compounds are pure and mixtures are impure. But then you mustn't go and confuse it with the impure properties. All right, so mixtures, components may be separated by physical means. That means there are no chemical bonds that you make or break. That would be filtering, using a magnet to pull out magnetic stuff, dissolving one thing in a solvent where another one doesn't dissolve and filtering it off, etc. So compounds can be separated by physical means, no chemical bonds. Because there are no chemical bonds between the different constituents, their amounts can vary. I can take a cup of water and I can add 1 spoon of sugar to it, and I will have sugar water. It's a mixture. I can go and add 2 spoons of sugar to it. I've still got sugar water. I can go and add 10 spoons to it. I've still only got sugar water. The concentration of the sugar is increasing, but it's still a mixture of sugar and water. So we say the composition can vary. It's not fixed. It's not like if I have water, the composition of water is always 2 hydrogens to 1 oxygen. There are no chemical reactions that take place when a mixture is formed. If I take my iron and my sulfur and I mix it up with my spoon, I've still only got iron and sulfur. To make it react chemically, to get the chemical bonds between the iron and sulfur, I needed to heat it fairly strongly. And then we can see there's a chemical reaction. But before I start heating it, there is no chemical reaction. All right, so no chemical reactions take place when we make mixtures. In other words, will it become hotter or colder? The properties come from the individual substances that make up the mixture. If I have water and I have sugar, sugar is sweet, water is fairly tasteless, so if I add the sugar to the water, it gets a sweet taste. All right, which is a mixture of the two properties. All right, compounds. Compounds may be separated by chemical means. I can take water and I add a little bit of acid to it, and then I can take 2 electrodes and connect it up onto a power supply, and I can make water break up into hydrogen gas and oxygen gas. All right, but I need electricity to do that because I need to put in quite a bit of energy to break up the compound, because I must break chemical bonds and new bonds must be formed. All right, so we can separate components in a compound using chemical reactions or chemical means, because we must break chemical bonds. Sometimes it's very easy to separate the parts in a compound, like water. It's very easy to do that. We can do it in a laboratory. You don't need a lot of energy to do that. Other compounds, something like aluminium oxide, is actually quite difficult to break up, because it requires a very large amount of energy. So depending on how much energy is needed, some things are easier to separate than others. The composition is always the same. Water will always be H2O. Vinegar will always be CH3COOH. Table salt will always be NaCl, sodium chloride. The moment we have different amounts, then we no longer have that substance, it's something else. When a compound is formed, there are always chemical reactions, chemical changes. So if I start with iron and I take sulfur and I make it react and I get iron sulfide will have its own unique properties. Okay, totally different from iron and sulfur, because chemical changes have occurred. Melting and boiling points would be different, for example. Then when we make a compound, new properties are formed. If I take hydrogen gas and I make it burn with oxygen, it burns with a blue flame and it produces water. All right? So new properties are formed. I know, for example, that hydrogen is a colorless, odorless, tasteless gas. Oxygen, colorless, odorless, tasteless gas. Hydrogen is less dense, oxygen is slightly more dense than hydrogen. But water, it's not a gas, it's a liquid with a fairly high melting and boiling point. Right, so we have new properties that would be different from the components it was made of. Definition of a crystal lattice: orderly arrangement of particles. Once again, those particles can be molecules. If I have iodine, a crystal of iodine, the orderly arrangement of the particles would actually be an orderly arrangement of molecules in the crystal lattice. If the if the solid was sodium chloride, the particles would be sodium ions and chloride ions. Do you follow? All right, so it doesn't matter whether it's molecular or ionic. A crystal lattice is simply the orderly arrangement of particles, the particles being atoms, ions, or molecules. And crystal lattice we get in the solid state. In liquids and gases, the particles have partially overcome the attractive forces and they move randomly. So there's no order to their arrangement. Now this lattice, this crystal lattice, can be molecular, okay? That would be something like iodine. Remember, iodine is a diatomic molecule, and there's another iodine molecule, and these molecules will be arranged in an orderly pattern known as the crystal lattice. Okay? That would be molecular. The giant that they refer to would be something like diamonds. Diamond has got 4 bonding places because it's made up out of carbon. Each carbon is bonded onto 4 others in 3 dimensions to form a very big structure. We get tiny little diamonds, they still contain carbon, and we get bigger diamonds, they also only contain carbon bonded in a specific way. All right, so then the amount can vary. But we talk about giant covalent structures, and we will have a look at them also a little bit further on. They say in a giant lattice, the pattern is repeated endlessly. For example, in sodium chloride, I can get a tiny little grain of sodium chloride and I can grow big crystals of sodium chloride. It's just a pattern that is repeated in a bigger crystal. Alloys, molten mixture of metals, as we've said the other day, just previously, of other metals or carbon. In alloys, the regular arrangement of atoms, in other words, the crystal lattice, is disrupted. And here I have a picture of what it can be. Here I have a very orderly arrangement of particles. And then this pattern gets disrupted because I have a bigger particle in between. This would be, for example, a carbon atom between sodium ions. Okay. Here's just another picture to show you. Here we have our orderly crystal lattice that is very definitely disrupted by different sized particles. And that is why, in general, alloys are harder, less malleable than pure metals. Why are they less malleable? Malleable means they can be pulled into threads. Why can they be pulled into threads? Because these layers, Yes, malleable, same thing, malleable and ductile. Ductile is drawn into threads, malleable you can heat it with a hammer without shattering. But why? Because these layers in the crystal lattice can slip over each other. But if we have alloyed it, there are different sized atoms and the layers get stuck, they can't slide. Alright, so alloys generally harder and less malleable. People, properties of alloys, they are usually stronger and harder and more resistant to corrosion, rusting. They are also poorer conductors than pure metals. Why would they be poorer conductors? Well, in a metal that is conducting electricity, the electrons can move because there is a specific orderly arrangement. So the spaces are orderly as well. But if I go and disrupt the pattern, if I am an electron there, there's going to be more friction. It's going to bump into other particles. So that metal will get hotter because the energy of the electron is going to be converted to heat in the particle that's going to be able to vibrate more. All right. So it will be a poorer conductor.
There's no price like the ShopRite price, which means you'll get low prices on everything you need. Like 1 kilo Jungle Oats, only $29.99. And a pack of 105 Roses tea bags, just $42.99. The ShopRite price, the price you can trust, always.
Win free airtime with hashtag #LearnOn1. Share your comments on the lessons. SMS your feedback, name and town to 555. Hashtag #LearnOn1. Invite learning in. Win free airtime with One Africa TV. Share your comments on the channel. WhatsApp your feedback, name and town to 081 200 6659. One Africa TV, it just gets better.
That brings us to Unit 3. There we go. Unit 3, the heading is Isotopes. Who can give me the definition of an isotope? Yes. Atoms of the same element, in other words, they've got the same number of protons, but they've got different mass numbers, which means the number of neutrons. When they ask the definition for isotopes in a test or an exam paper, we had specimen papers, they give isotopes 2 marks. So when we were discussing it, everybody gives the definition of an isotope: atoms of the same element having different numbers of neutrons. 100% correct, 1 mark. Because they want you to explain atoms of the same element have the same number of protons. All right? So isotopes, atoms with the same number of protons, same atomic number. So please state it like that. Having different mass numbers, which means the number of neutrons differ. Otherwise you're going to lose 1 mark. All right. Okay, the definition of an isotope. Atoms of the same element. Let's do this in a different color. Atoms of the same element, in other words, they've got the same number of protons. There we have it, same number of protons, but they've got different numbers of neutrons, in other words, different mass numbers. Please, especially if you see the definition counts 2 marks, explain atomic number and mass number. Do you understand? Okay. Now, we've done isotopes in grade 8, grade 9, and this year we have to go one little step further. Now, some isotopes are unstable. The reason being is the unstable isotopes often have more neutrons than the stable one. It's as if the nucleus becomes too large and it makes it slightly unstable. Now, when we get unstable isotopes, we find very often that they give off energy in the form of radiation. All right, uranium-238, isotope 238. Remember, uranium has got 92 protons. The mass number is 238. But there's a 234 and a 235 isotope as well. But the 238 one is especially unstable. Now, in an effort to become more stable, this nucleus gives off some energy. We call that energy radiation, and we talk about they are unstable, so they tend to decay, all right, break down or change by giving out energy. Now, radioactive decay, not all elements undergo radioactive decay. For example, carbon. Carbon has got 2 very common isotopes, carbon-12 and carbon-14. Carbon-12, how many electrons does carbon have? 6, it's atomic number 6. So carbon-12 will have 6 protons, 6 neutrons. But carbon-14 will have 6 protons and 8 neutrons. This makes carbon-14